Hello, everyone. My name is Alistair Ross, President and CEO of Rockcliffe Metals Corporation. Thanks for taking the time to watch this video. I think the key aspects of the story you're going to hear from Rockcliffe today is why we actually wanted to innovate a small underground mine design, and then which aspects of the innovation ended up in our package and how we managed to integrate them. And then, what's left for us on the innovation side should our preliminary economic analysis that has taken all of these technical aspects and is coming up with what the economics would look like on one of these deposits being developed in such a fashion. What's left at the end of that, should we be successful, that we would still want to pursue as part of innovation in a feasibility study. So we look forward to sharing all of that with you in the next 20 minutes or so. As usual, there's some pretty interesting cautionary notes to be taken care of here. Specifically, we believe you'll really like the story on our technical aspects of innovation, but be cautioned, we don't yet know the full economics of what these will look like, and we would only anticipate knowing that in the next weeks or so, and by the end of the year we anticipate being able to publish our preliminary economic analysis where the economics of these ideas will be revealed. So who is Rockcliffe? We're an exploration company currently, but thanks to a large investment from Greenstone, a private equity company out of the UK in 2019, we are very focused on becoming a copper producer. The strategy we're following in order to do that is one of a hub and spoke. We have a leased mill in Wabodin in North Manitoba, and our deposits are surrounding that with about 120 to 150 kilometer radius of transportation via truck. So how would we develop a sequence of small mines and keep the mill full over a period of time is what we're after. And the deposits that we've drilled out, which is the key point around why we need to innovate, are all quite similar no matter where they are. They tend to be smallish in the 2 million ton type range. The grade we believe is quite high. It's copper predominant, but with pretty decent gold and zinc equivalency adders. And we're getting somewhere around the 4% copper equivalent grade in our deposits. They're all narrow vein. They're typically between 1.5 and 2 meters wide. And they're very steeply dipping 80 degrees to vertical. And so that size and shape, when you look at the 4% copper equivalent, says a traditional narrow vein mine approach does not provide protection for us in a low copper price environment, and particularly for a short life mine. So one of the things, in order to overcome the risks of low copper prices and these quite short mine lives, and the investment therefore, is we need to have very high margins available to us. They need to be quite available at the low copper price range, because a startup like us, we can't go underwater just because of the low copper price. And secondly, the big piece about that is we can't overcapitalize either. So it's an interesting conundrum for us, is how do we put all this technical innovation into a mine design but not overcapitalize and get really good margins. The key part for us is that because all the deposits are also near surface, in some cases outcrop at surface, and the fact that we have a leased mill at our disposal doesn't require constructions or any brand new permits, it just needs permitting to make it over from a nickel to a copper producer, we can actually get into production quite quickly. So the other thing is our technology needs to be available today and proven today. And then finally, on the one more important part about the capital piece is that given the short mine life, the mine capital needs to be reusable. We've got to take it from one mine to the next. We can't leave a lot of capital in fixed infrastructure back at the old mine. And so we'll talk about what all those implications led to as part of our design philosophy. Where are we? Over here is the Flin Flon area, the camp that served Hudbay so well over many years. All their land on this map is in green. Our land is in purple, but centered around where Hudbay is now focusing up around their Lala deposit in the Snow Lake camp particularly. They have other pretty good deposits up there too. But we are literally surrounding them in the Snow Lake camp, particularly with our rail, the Penn, the Morgan, and the Burr deposits. we're very excited by what some of these are showing up. And then you're going to hear a bit about the Tau deposit down here. This red line is indicative of where the limestone cover starts and then stretches and gets deeper to the south, no limestone to the north. And because it's under limestone cover, it's hard to see, through it, unlike here where you get surface outcrops. Here you've got to do more modern exploration technologies to understand what's going on underneath there, and therefore we think this area is very underexplored, and we're looking forward to, on the back of being a successful producer, getting a lot more exploration into these areas here. So, innovation. The key concept was get all ideas into the design phase, don't try and bolt them on later. Make sure the ideas as they come up match our values. We don't believe we'll have all the ideas ourselves. Network as wide as possible, ask our friends to call their friends and get it ripple out. We've had ideas flow in from around the world as part of this. And another key part is, for traditional methods for a narrow vein mine, there's some very, very good empirical laws that apply about, well, how much can you get out of a deposit, et cetera, that we believe deserve to be challenged, given that digitalization of an underground mine is now possible. And you have access to technologies that weren't around when those empirical laws were developed, that guided us so well for many years. So we definitely want to challenge the ones that are empirical in nature. The ones that are a little more physical, like gravity, we may leave to another day. And those principles then led us to these areas. How can we actually eliminate fatal risks in the mine? And where we can't, by design, how can we actually lower the probability of those fatal risks occurring in our mine, either through frequency or different protections or so on. Certainly, one of the key things for us in order to survive low copper prices, we can't be restricted to the range of 600 to 1,000 tons a day from a stope. We have to blast through that in order to get the operating costs available for low copper price environment to be economic for us. We certainly want to reduce variability and increase reliability. We can't overcapitalize. These are small deposits. We're a startup. The quality, particularly for us, we believe is another key to how we can get very good operating costs. And energy, as people are familiar with underground mines, energy is anywhere between 15 to 20% of an underground mine's cost. So we certainly want to look in that area, as well as materials and the people costs of running underground operations. And then the final aspect that guided us through all of this were the commitments that we've declared for the company that are in support of the 32 principles of the Responsible Mining Minerals Initiative. That's all about creating a sustainable mining future. And you can see for yourself where they are up there. So, some specific examples in the safety arena. One thing that we're very satisfied with is we've essentially eliminated raise mining from our operations. We don't have ventilation raises. We do not have ore or waste passes. And we think there's two aspects on the safety piece around that that we really like. The first is you eliminate the open holes from people being able to fall down. And the second is the actual active raise mining is one of the riskier aspects of underground mining. And if we don't have to perform it, clearly one of those risks is removed. So you'll see in our design later, we've managed to achieve essentially that, with the exception of one small 40-meter raise near the beginning of the mine development phase, purely to manage another safety requirement, which is dual egress from an underground mine, and what that looks like. And particularly for us, if we have twin ramps, the twin ramps have to be so far apart in order to be counted as second egress legally. And in order to manage a big initial capital, we put the two ramps very close together at surface and separate them out. So it's just where they're too close together for regulations, we've got a raise that's the second way out for us. Yes, so very interested in that. We'll talk about explosives later on. Then the probability of fatal risks is we've managed to separate completely ore haulage from personnel traffic routes. And as people know, a very significant risk underground is people being run over by equipment. So we're quite happy that the largest traffic areas are now separated. And then the other ongoing longer health risk is about diesel equipment and their emissions. And you'll see that if we go to battery electric equipment, that we've essentially removed that completely as a risk for us. And we'll talk about how that integrates later on with the energy strategy. And another interesting part that people might like is that we engaged with a psychologist very early on with our designs, knowing that we'd have remote camps distant in northern Manitoba. And what would we be looking at to have a camp design support an individual's mental wellness while they're in camp? And it was fascinating as we went through those conversations, how the conversation broadened to things such as, well, what's the best shift rotation? What data is available around people being on different shift rotations, and then their reported mental wellness or unwellness. And we were able to actually select a shift rotation that has got a lot of evidence to support that mental wellness is much better under that shift rotation than other shift rotations. The other key aspect was making sure in our selection of employees, what type of supervisor we wanted in there, and what tests we could do to have the appropriate supervisor to support people's mental wellness. And that wasn't clearly just about the supervisor, it was also about the superintendent and the managers. But so we've now developed much, we believe, improved selection criteria for employees. And then another critical part was around orientation, both into the company, into site, and then each orientation on the shift rotation coming in. So there was a lot of very, very interesting learnings there. And then we got into the accommodation design clearly, what type of pillows should people have, and what's the blackout curtain quality, stuff like that. And then the support while they're at site, make sure everybody's got enough broadband to do FaceTime or whatever version of video chats they choose to do with their families. So lots of good stuff there. We want to now talk about some of the environmental pieces. We've done as much as we can to make the mine site as small as possible so that we don't have to clear a large area. And a piece of that is, where does your waste get stored while you're still developing the mine and before you have the access to be able to put it back underground in the open stopes? So selecting technology that actually reduces the volume or mass, in this case we're interested in volume, of the waste rock. And that formed an important piece of our decision making. And it's our values about less impact on the environment. And that then needed to integrate itself into further conversations around, what if you've got small holes, what does that mean, et cetera. And we'll talk about how it's integrated nicely with some other very advantageous, both capital and operating cost aspects. And then of course, by deploying ore sorting at the outlet of the mine before we transport the ore to the mill, we're able to take out a lot of waste in the initial mines. Is looking like 40 to 50% as a minimum of the material we'll be able to put back underground with hardly any mineral loss at all. And that's a big, big deal for us, because the greenhouse gases to take waste rock on the road to the mill disappear. And then the greenhouse gases that are used, or as a byproduct of the use, as we grind, crush, float, filter, or in this case, not filter, but deposit in the tailings area, all disappear as well. And then of course, the size of the tailings dam diminishes by that amount, 40 to 50%. It's a huge, huge impact on the environment as well as the greenhouse gas stuff. Because we're in Manitoba, we're very fortunate. Most of the power in Manitoba is Manitoba Hydro from their large dams up to the north of us. And some of our deposits literally have power lines on them, and where possible, we'll be taking power off Manitoba Hydro, even though we have a very short mine life. So we're figuring out how to do that economically. And in most cases, it's not that hard, even with low diesel prices for gensets, putting a power line in does appear to be quite economic. And then, of course, our greenhouse gas emissions changed dramatically. We've electrified all the underground mine equipment either through direct electric on the railway drives or with battery electric vehicles. And what's interesting is that that has actually improved our costs of supplying electricity as well. So we're fascinated by that outcome. And then, as we spoke about lower transport costs, etc. Here is what the mine plan is beginning to look like. We'll have dual drifts coming down, separated as appropriate for dual egress. The red is the railway ramp, the blue is the service ramp. They're always interconnect points as appropriate to get you from one side to the other all the way up, but separated so that if one fails, it will not impact the other. So we're taking care of the safety aspects. What we have in addition to all of this is the sill level that you can see is the white layer just at the bottom here. We're going to do an evoker mining method at the top to take care of some crown pillar support issues. We'll fill back in here. Then we leave this sill pillar, and from here on we'll use the railway to actually bring rock back underground and a scoop to drop through finger razors into here to do the backfill underneath here. And this way our rock tech information looks like we'll have a very stable crown pillar to support all these large stopes that will occur underneath here. Each one of these would be a railway level where we'll take out the ore from the bottom of the stopes. We'll have a hag loader actually going in the stope and mucking out from underneath here. Railway then runs back out up the ramp, comes in here, drops waste back here, comes back, gets ore, etc. So we're very, very happy with what all this has entailed as an integrated design. And we're going to walk through what some of those results start to look like. And the key part is we're able to, by bringing fresh air down the service ramp, and then how it's distributed into the workplaces is people are always in clean air. There's no diesel underground, and then any particulates, etc., that are carried out go up the railway ramp. So there's no one in that railway ramp. It's fully automated, and so everybody's got clean air. We're very happy with that. So the loading from the stope onto the railway, on the right here, a couple of pictures for those who are not familiar with railway. You know, this is what a train looks like. It's just this tube. There's a second one over here in this particular picture. You can see this is a rather large excavation because it's been retrofitted in this particular case into an existing mine. Our openings are going to be a lot smaller than this, and we'll talk about that in a minute. But essentially the ore comes in here, and when it reaches wherever you want to unload it, you have a little dump unload. The rail cars go underneath here, upside down and empty. And then when it's finished, the rail comes back up and goes back to wherever it goes. Our particular case, this dump point will be up on surface, so no excavation required for our dump point. There will be for the waste, but because we're trying to dump down into something, it'll be rather smaller requirement for us. The interesting part for us is that the loader that goes into the stope, there are a few models available to us, none of them yet automated, although some currently undergoing automation efforts. And so we don't expect to be the first to run one of these on automation or teleremote, but we'll be amongst the first at all, and nobody is anticipating any issues on that automation. By utilizing the battery electric approach for all equipment underground, ventilation requirements have been cut by half according to our calculations. And there's some important aspects to that. It means that we can now carry the ventilation in our ramps and drifts, and we don't need ventilation raisers. So that's a big win for us. But it also means that our ramps are now much smaller than you would traditionally do. We certainly don't have any big trucks because we've got this low profile railway here. And therefore, we've gone for 4 meter wide by 3.5 meter high ramps, 2 of them. And what's interesting, 2 of them is actually less excavation required than a single 5.5 by 5.5. And if you had big enough trucks, you probably need 5.5 by 6 wide to get your trucks going there, along with the ventilation ducting required for diesel. And we haven't even yet taken into account the fact we're not constructing raises, because in your 5.5 by 5.5 or your 5.5 by 6, you have to add ventilation raises to make it all work. So just on the ramps alone, we saved, and then you save additionally on the raising. So very, very good result for us. Integrates a number of things together. We've spoken a lot about the battery electric piece. The one part that I want to talk about here is that if you've cut your ventilation horsepower by 50%, the amount of heating required in those cold Manitoba winters where we get -30, -40, -50, I don't want to mention, but it gets cold up there, is that the amount of air going in the mine is so small that we double checked a few times, do we really only need that much heat? And therefore the greenhouse gas required for this mine drops again, because we have to bring in an LNG or a propane or something like that to provide the heating for this. And so the amount drops very dramatically. And the overall horsepower required to run the site, the overall energy consumption of the mine drops dramatically. So what's left for us? We're looking at building the digital mine and constructing the physical twin. We believe that'll give us a lot better control, both during construction and operation. If anything unknown comes, we can run against the model and see how we can still optimize NPV and IRR for the overall investment very, very quickly. So it's the opposite of people who've already got their mine and trying to construct the digital twin. We're looking at digital safety platforms. We're very happy with what's evolving there. We think there's a lot of opportunity for us to have people not access pieces of equipment because they get locked out electronically. They don't have their up-to-date qualifications, etc. Plus how work arrives for them. And then if they need help, they can show video right up to surface, or workers in the mine say, hey, I've got this problem in front of me. What do you know about it? And communication we just see is really important to assist future safety enhancements. We spoke about how could we get rid of explosives. We're part of a relatively large group looking at mechanical rock excavation, both for the ramp, the drift, and the mining. And therefore, can you take out one of the fatal risks of a mine altogether with no explosives? So we think that's got some interesting hope for us in the future. It won't be in the first, probably won't be in the second, but maybe in our third mine by then we would have done enough work that explosives have disappeared. And finally, around explosives, what we're very interested in is, can we remove people 100% from the face so that there's no one exposed at the face? Big safety advantage. And the last piece that's actually needing to be resolved to get that done, because everything else is there already, is how do you remote load the explosives in your development drift phase? And we've got some interesting technology. We're in another consortium that's doing that work, and we're gathering the data on that now. And what's fascinating, as the cycles improve, yes, we believe we'll be able to get people away from the face, but we're also seeing the potential to actually shorten the development cycle and get to the ore faster. So a wonderful attribute of improving the safety and productivity at the same time. And whilst that won't be available to get in our PEA, there is still some thought that we can get enough data that it will go into the feasibility study should our PEA economics come. So that's it for the day. Thank you very much for listening to Rockcliffe. And we look forward to telling you more of the story as the economics come out in our upcoming PEA publication by the end of the year. So thank you very much for your time, and we hope to talk to you again soon.